So I'll let Jamal get us started.
Yeah, so we feel this is a very important topic. Jess is going to do a tutorial. Pedro and I, and Nabil Bitar, who's not here, have done a lot of work on doing performance testing on networking as associated with power, right? So we'll do a presentation on just how to collect power metrics. And then Marcelo is going to present some numbers at the end, if there is enough time.
Oh,
yeah.
Hey.
Okay.
Hi, I'm Jesse Brandenburg. I'm a longtime device driver engineer working on drivers, and I've done a lot of performance tuning and work on power stuff. And in fact, a couple of years ago, we did a presentation about power management, and I'll talk about it briefly here during this tutorial. So what are we going to cover today? And I'm going to go a little bit fast because really I'll let you read the slides and I'll talk to some of them. So yeah, we're going to talk about power management and a bunch of stuff about why it matters for platforms. And then there's some ways that you can actually, some tools that you can actually use to go look at your power management on your platforms and try and figure out what's going on and how they interact with the Linux kernel and how they interact with you, the user. What's power management? Really, you just want to save power, right? You want to have your platform not either run so hot or need so much cooling or it's going to try and use less watts so that it can end up being either more efficient or save you some money, whatever, at the end of the day. But oftentimes you're less asking this question, what are you willing to sacrifice for power management, right? Are you willing to sacrifice latency throughput? So you end up having to think ahead about what things you're willing to trade so that you can get maybe a little bit lower power usage. We'll talk about the different terms here in this space are the CPU, the RAM, and the uncore. You'll hear me use this term a lot. It's about the uncore, if you haven't heard of it, is what Intel calls what used to be called a south bridge in a lot of platforms. Or the north bridge, rather. I'm sorry, I used the wrong word. The idea is that this piece of the CPU is now responsible for the DMA controller and the memory controller and the cache controller, at least in the Intel CPUs. When I'm talking about adapters here, there's a bunch of different ways that you can manage power with adapters as well. There's things like energy efficient Ethernet, which I'm not going to talk about, and there's ASPM, which I'm also not going to talk much more about than right here. And you can also turn off your link if you really want to save power. So like if you have a laser optical module, uses a lot of power all by itself, oftentimes more than the ASIC, just to keep that laser up and running, right? Lasers aren't exactly super efficient. The other ways that you can manage power on the platform have to do with frequency changes, like for the CPU and for the RAM. And you can also use this thing called P states, or C states, which is actually the core states of the CPU. So we'll talk about these a little bit, right? What can you use to manage the CPU? And I'm sorry for the tiny font, but hopefully it's big enough on the big TV. Your C states are about the core states. This is basically stopping the CPU from executing instructions. And you can change how long it takes between when it wakes up. So like a C1 state or C1E might take a microsecond to wake up. And something like a C6 state, which is these are terms that Intel uses and are pretty common, I think, across the industry. They might even be standardized, but the idea is that like C6 might take 125 microseconds to wake up, which is a really long time in terms of like 100 megabit or gigabit networking. 100 megabit networking is not so much. For P states, this is managing frequencies in the processor. So the processor is constantly doing P state management, and I think Jamal will talk about it a little bit. It's trying to manage the frequencies to reduce them whenever possible and speed them up when it needs to go faster. And this includes turbo management, right? So the Intel processors have this idea of turbo, and if you've got thermal envelope on your CPU, you can actually speed the frequency up beyond the rated amount and run faster. So your 2.6 gigahertz processor might be able to run at 3.5 gigahertz or 4 gigahertz for short amounts of time, or when there's not very many CPUs running at the same time. If you haven't heard of it, ASPM is Active State Power Management. It's basically powering down the PCI Express link, which PCI cards do take power, but as far as the grand usage of the system, your PCI power on the slot is probably not your big deal. It's small fry, like 10% of the system or less is going to these PCI adapters. So we're talking about watts measured in tens of watts for the PCI link to stay up. It's a serialized serializer link, and the more lanes you have, the more power it uses, almost perfectly linearly. But nonetheless, if you want high-speed I/O, you have to pay the cost somewhere, and having it connected to the bus there is that cost. I'm not going to talk any more about this IEEE. It's a standard, or sorry, EEE, which is energy efficient Ethernet. It's the idea to power down the link, but this is really only on client platforms, powering down the transmit logic to make sure that the device is saving as much power as possible. Makes a lot more sense on a laptop, not so much in a server. I already talked a little bit about the uncore and the power states in the processor, but the uncore has its own power states called PC states or package C states. And when the CPUs are all asleep, then the uncore can go to sleep. So it's kind of a progression, but the uncore, when it goes to sleep, there's no more DMA. Your PCI devices no longer have access to the main memory because the uncore owns the main memory access for the DMA devices. So if you get into a PC state and it has a really long wake-up time, like 150 microseconds plus, then that's time that's delayed, that's time to delayed where the DMAs can't run. So now the only thing that's able to store any data for an I/O device, like a network card, is the little tiny memory on the card that's usually called a FIFO. And we have like maybe a few microseconds worth of storage there at 100 gigabit, or at faster, it's gonna be less. So it's a big problem when the PC state is engaged and you have no access to DMA. Let's talk a little bit about why this kind of stuff might matter, right? This is a pure hypothetical, and I'll be honest with you, my math may be a little bit off, but I tried to make it as accurate as I could at the time that I wrote this slide, right? If you have 10,000 servers and you have a whole bunch of top-of-rack switches connecting all these servers together in the data center, if you're able just to save 10 watts per server, you may end up being able to save as much as like $9,500 a year, which could buy you a couple extra servers. So sometimes even just doing a little bit of power savings can end up being a big lot of money when you start doing it across large scale, right? And the data centers in the big data centers are all about large scale, right? So if they're willing to make the sacrifice on something, they may be able to manage power better. And also, this doesn't account anything for cooling in the data center, which is as you burn more power, you have to cool more to keep your machines cool. And it also doesn't take into account all the other things like all the switches, et cetera, that may have to be involved in keeping this data center up and running. So just a good example, a little bit of power savings, which is 10 watts out of a 400 watt or 1200 watt server, doesn't seem like very much, but it can turn into a big bunch of money. This is a really important point I like to make, which is that high-speed Ethernet is really the only surprise-driven device in the entire server, right? It's the only one that's driven asynchronously, especially for high-speed I/O. So yeah, you have asynchronous input from your keyboard and mouse, but that really doesn't count in this context, right? And especially for a server. So this is really relevant for power management because the machine has no idea that the traffic is coming. So oftentimes, and the discussion I'm wanting to have here is how well can the networking stack have some kind of heads up for the platform because it knows that there might be traffic coming, or that there's more likely more traffic coming because there was an active conversation just recently. That stuff's not taken into account at all today. So you have this surprise I/O, and everything is having to wake up, possibly from package C6, which might take hundreds of microseconds to wake out of, right? Which would really suck. A big point here I've been making, servers are way different than laptops. they're big power consumers, right? They have a lot of pieces. I already talked about some of these: power supplies, processors, lots of RAM, hundreds of gigabytes, plug-in cards, lots of I/O, Ethernet, lasers, fans. Fans use a lot of power. So as your machine gets hotter, the fans have to run faster, and that often isn't taken into account. I had actually tried before this talk to get our power PDUs hooked up so that I could measure and show you the difference between what turbostat reports inside the platform and what an external power meter reports that the power supply is using and burning, and the CPU's fans are using and burning, right? So that you could get a feel for what the difference was. But unfortunately, that data didn't come up. I really apologize ahead of time. But it's a good data point that the internal reporting mechanisms of the server are only so good to the pieces that they're paying attention to. And we'll talk about that a little bit more when I get to the slides and talk about the tools. Let's talk about tools. Tools I use when I'm trying to figure out power and latency stuff is turbostat. Jamal brought up this Intel PTAT tool, Power and Thermal Analysis Toolkit, I think. And it's an Intel design tool that you can download if you have some kind of a relationship with Intel. There's also a whole bunch of things like the GNOME Power Manager and PowerTop, and these are all often client tools. They work on servers, but they're not as useful. They're really targeted at like turning off all devices on a laptop to make it last for 12 hours or plus, something like that. And of course, there's external power measurement, like I talked about before, and I mentioned a couple examples here. So what do we do for control? Our CPU frequency subsystem in the kernel is able to control a whole bunch of pieces about power, and it's kernel interface, so it's processor agnostic, and it depends on the architecture implementation for each arch. There's also a power aware scheduler, and the schedulers are aware of what's going on at the user space and at the platform level, but they don't pay much attention to networking, which is a big gap in my opinion. One of the reasons I wanted to come here today is to point that out. There's this tool called CPU Power, and this tool comes with the kernel. It's actually part of the kernel source in the tools directory, so you can build it yourself if your distro doesn't have it. There's a couple commands here that I mentioned, this idle info, idle set, frequency info, and frequency set that let you have a look at what your processor is capable of providing from the side of the kernel's interfaces. There's also these sysfs directories, and this is actually what CPU Power, I think, is using from a user space side or something similar. And nice. So the whole point of these directories is that you can actually go look at them yourselves. The other thing is that there's scripts like this GitHub project that I mentioned here that allow you to modify your CPU frequencies and play with the controls over the CPUs that the kernel gives. So what do I have, right? You can run this command, CPU Power idle info, and it will tell you about the C states that you have and what you can do with them. It will give you a list of the C states themselves, what they're named, and how long their exit latency is that the kernel knows about. So the CPU Power command deals in terms of microseconds, which is why it's useful and agnostic to the processor. So if I give it the command CPU Power idle set -D10, it's saying, I would like you, Mr. CPU, or Mr. Platform, to keep your CPUs awake so that they have no worse than 10 microseconds of wake latency. So that's what that command does. When I ran that command on my Sapphire Rapids system that I have sitting back in the lab, my power utilization went from idling away at 67 watts to idling away at 137 watts, right? Just that one little command to say, sleep less, right? I was sleeping at 125 microsecond wake time in C6. My system was idle. I changed it to 10 microseconds maximum idle time, and the power usage went up quite a bit. It's an example of what the command does and how it works. So this should work on any CPU that the kernel recognizes and knows how to power manage. If you have a really old distro and a really new CPU, it's likely that these commands won't work. So just be aware of that. It's a caution for you. right? You got to make sure that your kernel's recognizing the CPU that you're using. There's a lot of things that can go wrong in power management. And one of the reasons debugging platforms is so hard is that there's many, many pieces to the puzzle and a lot of moving parts. So like I can mix a ton of analogies here, but the problem is as you optimize for power, you often either, if you're trying to save power, you probably are sacrificing latency. If you're trying to be just a good power consumer, you may actually end up hitting throughput. And I've seen both cases, right? Because what happens is as you're, you run into buffer bloat problems, mentioned for Dave there, right? I was one of the hands raised earlier. I know what buffer bloat is. You can cause the RTT to go up because your latency is so high. So now your round trip time to the remote stations has gone up because every time you send a packet, your CPU goes back to sleep, and then surprise, a packet as it comes back on the response. The networking stack is giving no indication to the kernel or the platform that it just sent something and is expecting a response. It's kind of lame, right? We should probably try and fix this. I've been wanting to try and get to this for a while. So I think we should do something about it now. I think it's becoming more of a concern as processors start using more and more power. A way we used to deal with things in the past, and it's still written down all over the place in documentation, is just turn off power management. Sure, just burn 1,000 watts when you're idle. No problem, right? Well, there might be little problems, right? The first one might be that your data center overheats. The second one might be that your CPU's lifetime is probably going to be a lot shorter because the heat load in the platform is going to be big and large, right? And it's just, heat is bad, right? And yes, the processors are designed to handle it, but they also don't like being hot for, 365 days a year, 24 hours a day. Polling. We know about busy poll being a thing in the kernel. There's also user space polling, right? We can poll. We can use lots of CPU. We can have very low latency, which is fantastic, especially if you're a high-frequency trader, but you're going to sacrifice something. In this case, the sacrifice is I'm going to use a lot more power. So these are both draconian. They kind of generically apply across the entire system. Same thing goes for bias changes and settings. And when we have really big systems with hundreds of CPU cores or threads available, it doesn't make sense anymore, to me at least, to tell my platform, just in case, let's burn a lot of extra power, maybe 10x power of what you need to get your workload done, right? Because you might have an idle system that could idle for a few hours a day, or maybe it's idle for minutes at a time. Figuring out some kind of benefit to turning on the power management. The other thing that you get from turning on power management is your thermal envelope is very large, okay? So imagine that I have a heatsink on my processor that can dissipate 1,200 watts and fans that can handle it. Great, it's fantastic, good design on my system. Thing is if the processor's idle, it can actually bump the frequency up on some of its cores and use even more power on those cores that are the only ones that are busy in the system. So let's say I have 2 cores that are very busy doing some networking traffic, and I haven't just let my system spread the work out everywhere, right? I've concentrated it down to a couple of cores. This allows your CPUs to actually run faster than their rated speed, which means that your threads are now quicker and getting done with their work faster. So this is a good thing. You could even have those 2 CPUs maybe only have a 1 microsecond exit idle time and have the rest of your processors in C6. But today, you can do that with CPU power, but there's nothing that kind of manages this stuff automatically, right? It's either the processors are just being allowed to go all the way into C6 or, and especially with networking, right? We really want to have a change to make the networking tied to the power scheduler and the platform so that you can get good performance out of your networking or great performance out of your networking and save power. I think it's possible. So I already mentioned bias settings, and then there's this ancient interface that was made out for client CPUs called CPU DMA latency that if you open it with a user space program, you can say, I would like you to keep the whole platform awake, which is not super useful when you've got 224 CPUs. I'll give a plug to my previous work from Netdev 15. Brett Creeley and I made a presentation, actually a proof of concept that had a script that we still have never published. I'll blame somebody else at Intel for that one. No, it's my fault. But the point is that this work showed that we could manage power via a bash script and these kernel interfaces that allowed us to shrink the number of queues that traffic was being directed to when the system was idle, and then only grow those queue usage on demand when the traffic would increase. I think if we took this to the next level and brought that functionality into the kernel, this would be a great step for doing this more active power management for networking. So I have thoughts. I'm sure you have lots of thoughts as well. We already talked about this some. How do we make the networking stack give more feedback and participate with these existing things that are already in the kernel today? They're just not talking to each other. One idea I had was, can I keep the stack, can the stack keep the CPU awake a little bit longer? So for instance, the stack just received some traffic. It knows there's maybe more coming because it's got an open TCP socket. The application just ran. It's still busy, right? Maybe the networking layer, the socket layer, should tell that CPU, hey, stay awake a little bit longer. Don't quite go back into C6. Let's hang out for a little while. Not poll, just don't go so far into sleep, right? There's a difference. So busy poll would have taken us busy polling that CPU, keeping it at 100% utilization in C0 until the timeout hits, which could be very long. And by the way, the timeout's not per CPU, it's for all the CPUs. So yeah, can we make a change there to make that better? I want to make a power aware stack. We already talked about busy polling, and maybe we could take the idea that was actually just presented by Amrita an hour or so ago of having queues that are known by the kernel and controlled by them. Could we make this power policy part of the queue model? That's a possibility. And like I said, we're missing the granularity that we need in the kernel. We need some new kernel interfaces to control some of this stuff that we already have control over, but it's not granular enough to be able to be controlled, especially from driver level. A lot of these interfaces are in sysfs, and there's no kernel calls, no functions exported for us to be able to call from a driver or the stack. So that's another small problem that we can probably get a hold of and fix as part of this solution. The other thing is that it kind of sucks, the scheduler delay being around a millisecond. That's a long time at 100 gig networking speeds. That's like hundreds of thousands of packets arrival kind of timeframes, right? Or millions. So that's a really big problem for really high-speed networking, and it's worth just mentioning that maybe the scheduler, we need to figure out ways to interface with the scheduler better when we're having a high-speed networking conversation. Not all the time, just when we're doing high-speed networking. All right, just about out of time, and I would like to say, email me or come join this new mailing list that the Netdev Society just created for me called NetPower. If you would like to talk about this stuff, I would love to have a conversation with you. It should be pretty useful to be able to move forward. I would love to help drive myself this idea forward. So if you're interested, come help, please. Let me know. I see a hand. I'll get to you. Just one more. I had a couple cool similar links if you wanted to go look. They'll be in the presentation deck when it's uploaded on the website. Other people talk about power management too. And here's a few links that I found.
Should we wait until the end for the discussions, or you want to take them now?
Your call. I'm done with the presentation.
Yeah.
So I have maybe a high-level thing, and let's
Sure.
inject it now, and then you can maybe address it. So I think there is a couple of things that I think you have to think a little more broadly. All your statements are around 100 gig networking.
Or 200 or 400.
CXL will bring this in spades. The problem that you're talking about is a very simple problem, which is a scheduler thing.
A very simple scheduler. Did you just say that?
It's a scheduler interface that you need. What you need is something that says I/O has an ability to tell the scheduler that it's not just about managing memory and your threads. I'm going to do something that you need to pay attention to. And you can't do it the way you were even suggesting it, which is to say, if I'm going to transmit it, keep me awake, because it might be on a different core. You might be signaling for an asymmetric operation, which may or may not actually be the right thing to do. Plus, as you know, package controls are not specific to threads or cores. It may be tiles, it may be all kinds of things. So what you're really, I think, advocating for is a more generic scheduler hint, and which has to apply to multiple scheduler patterns, that says, keep me alive, and I'll tell you for how long, and trust me, I'm correct, because that's the tricky part.
Yeah, yeah. I mean, at least the kernel interfaces today, by the way, I totally agree with you. The kernel interfaces today are generic and CPU agnostic, which is nice, right? They deal in microseconds, which is pretty good. Better than milliseconds. But we need to make some small tweaks to the interface so that we actually have some accessibility within drivers in the networking stack. Yeah.
So check.
Yeah,
There we go. So 2 quick points. I've been around for a long time, but I wanted to ask the audience, has anyone here ever heard of the Caltech asynchronous microprocessor? It's remarkable how much
Yes, I have.
one person.
Yeah, we got somebody.
I thought in 1989 that was the future. It scaled up and down beautifully without P states. So look at that as a design path we could have gone down on. Caltech asynchronous microprocessor. However, the core point I wanted to make about scheduling is it is complicated, and there was a group working on a coupled power and rate controlled scheduling called Minstrel Blues about 8 years ago. And I think the algorithms might apply here.
Sorry, ask that again, Dave.
Yeah.
That was just a statement.
Okay.
Go looking for Minstrel Blues.
My observation is that many people have lamented for a long time that too much of Linux networking runs in soft IRQ, and the scheduler people have no control over it. So at some point, I think we may have to bite the bullet and take the latency hit of not running network in soft IRQ and switch to running in a K-thread, where the scheduler at least has a chance to see you and know what's going on.
Yeah, I totally agree. And in fact, threaded interrupts and threaded IRQs exist today. They be turned on per interface, but they're not default on.
Right. That's
I think ripping more code out rather than adding more is a really good strategy. And where did Nappy 64 come from anyway?
I have a question / statement. So,
Sure, go ahead.
Are you aware of work that Facebook has been doing on SharedX, like an external pluggable BPF scheduler? And because you mentioned how the scheduling delays for high-speed networking is quite unacceptable.
I am not aware of that. I'd be very interested to see.
Yeah,
that.
definitely, because I think we're also internally looking at applying SharedX to
I'm sure
like
this-
high-speed networking applications.
Yeah.
How to make the scheduler more smarter, because, like you said, the current delays are quite unacceptable.
I believe there's probably a lot of work happening in a bunch of different spaces that's all relevant to this problem, because it's not going to be a single point solution. It's a bunch of like little incremental steps that we'll take that would make the problem slowly become less relevant, right? Because it's certainly not a one fix to fix everything. If I've learned anything over my years, it's that nothing's simple.
Yeah, so I think, can we hold on the questions? Because we have 2 more presentations, and it's Thursday and Friday. This is a very interesting topic. We thought it was important enough to bring it here. Okay, so, all right, I'm going to go next. Carl, can I get the screen? All right. Okay, so this work is done at a large enterprise called Bloomberg. So Nabil Bitar, who's not here, I think he's virtually connected probably. Myself and Pedro, starting right there. One of the earlier, so you probably may have guessed, I do a lot of offloads. And so this is where this started. So it's a very hard sell to tell somebody, I just saved you 30% CPU or 40% because I offloaded something. But it's a much easier story to tell them how much power you saved them, right? So that's where this came from. And we experimented with a variety of DPUs or IPUs, depending who the vendor is. So it's a powerful story to be able to tell somebody, look, I just use PCI 3 NIC, which sucks 45 watts out of your system, and I just saved your CPU 200 watts. It's a much more compelling story to tell. So that's the background, okay? Motivation, basically, AI, for sure, I'm going to start with the last bullet, is driving a lot of this with machine learning. A lot of compute power is being put to task today to solve these problems. So the data centers are growing, in some cases, exponentially or tremendously, maybe is the right word. If you want to think about it from an altruistic point of view, you want to save power, so to save the environment. And offload is hitting mainstream, so the PCI devices, there's a lot of PCI if you look at the chiplet approach, where a lot of these things get removed from the main core, or you have special purpose cores. So there's a lot of motivation. And chip vendors are deploying the P and E cores, Sapphire Rapids being one of them, to trade performance versus efficiency. And while we were doing this, we thought this was going to be a quick exercise. It turns out there's a lot of magic in the CPUs. I think Jesse touched on some of it. Just because you decided you want to use only 4 cores doesn't mean your power goes down. The package just is so smart, it just starts adjusting your frequencies, and your power consumption goes up. So we had no idea how this stuff works when we started. We were very naive when we started, and it became a topic, essentially. So sources of power, most of these were mentioned by Jesse. The CPU, if you write really bad code and you're consuming 100% of the CPU, you have locks all over the place, you're really consuming power. Fans, DRAM, there's a improvement in how much power DRAM sucks. PCI devices, if you have a NIC, some of the modern NICs require extra power. They just don't draw power from PCI anymore. They're like GPUs. You have to suck more power out of the board. Disks, core processors, this whole chiplet thing is coming up. So QAT, for example, on Sapphire Rapids, which is supposed to be very friendly, and many others. Okay. The purpose of this is to say, can we rethink networking instead of saying, I'm going to get 10 million packets per core? Can we say, change that mentality and say, can I get 10 million packets per watt as the metric? Because Marcelo is going to talk in his next topic, I think he says, not all CPUs are the same. If I'm measuring ARM versus AMD versus Intel, and I'm getting 10 million packets per core, they are oranges and apples. They're all fruits, but they're different fruits. Right? So we want to change that mentality. Right. So our focus here today for our presentation is how did we measure power? And we hope we share this with the community so other people can benefit. And it took us a while. We had no clue on how to do this. So half of this was mentioned by Jesse already. You've got, I like to call it ACP. Some people call it SCPI, which has sensors. LM Sensors uses it, power top. And you can get SCPI measurements for the voltage of the power supply, for example. You've got external devices, which is eventually what we ended up using mostly. You've got BMCs. Usually they have sensors built into them. And the best tools are proprietary to the CPU vendors. So PTAT, PTAT, which is the Intel one we ended up using. You can also get tools to measure power within a DPU or an IPU. And believe it or not, you can actually buy a piece of hardware that you plug onto a PCI bus that will measure power for how much each of the PCI devices use. Okay, so here's an example of some of the measurement we did. So we were running in, you're going to have to correct me on this, we're running in what is known as power saving mode. And so you see the first few seconds there, the system is warming up. And there's two measurements. This is drawn, the green comes off the ACPI measurement. It's measuring the power supply on the system. And we found it was quite inaccurate. It was flip-flopping back and forth from different levels. The external PDU, they call them PDU, is the blue. You can see that those are measurements we took. And the red line here is when the system was idle, right? So we ended up abandoning the green. We didn't use green. We just want to measure how much the server is consuming. This includes PCI bus and everything else underneath, right? So we gave up on ACPI, or the power sensors, basically. Now, our test setup, we have two machines. I'm not going to talk a lot about details of what the test looks like, but we have two machines. We have a Cascade Lake, which is a Sika 2020, which had 26 cores or 52 hyperthreads. But we're poor, so we only, well, we're not exactly poor, but this server had only one core, one socket instead of two. It is SMP, it's a Supermicro. And then on the other hand, we have a Sapphire Rapid, which has 56 cores or 112 threads. One has 128 gigs of RAM. And these tests were conducted using Bluefield 2x25 gig links. Okay, this is how so we ended up, I have to say we were very naive. We didn't know these things. Maybe we could have talked to you. So we ended up finding a company in Prague, in the Czech Republic, that has this device. You can connect up to 4 sockets. It has an Ethernet, and it provides you a HTTP endpoint to query what's going on the system. As a caveat, so that's the company name. You can Google them. This thing costs about $400. The connectors are very interesting because they are not your regular power connectors. There's a C13 and C14. And this thing claims to measure up to 99.9% accuracy, 99.99. Now, ACPI on the system, I think, is about 97%. So that will account for the discrepancy. One of the servers has a BMC, and it exposes what's known as a Redfish HTTP. The other server has a BMC, but they wanted us to pay a license fee. So we couldn't control much to do with it. Okay. So here's a sample. I think someone was interested in KTLS offload, so that was the easiest thing for us to test. So you can see on one side here, we're measuring the temperature and the fans from the BMC. At the bottom here, you see the temperature. As the temperature goes up, the fans start kicking in. This thing was very loud. It's almost like it's a helicopter about to take off when it hits this many RPMs. And then this temperature stabilizes. And you can see then the fans start to gauge where to stay stable, and eventually they're stable. On the one side, the average of the power utilization of the system, not necessarily the CPU, we have numbers for the CPU as well, is in the range of close to 500 watts, right? And the instantaneous values are 5 milliseconds, I think, was a polling period. You can see that is the instantaneous, and the green is average. If you look at the bottom here, is this CPU utilization from system all the way to user space, right? And if you look at the perf output, because this was KTLS happening in the kernel, you can see the biggest culprits are the encryptor. The top one there is encryption. You repeat this by offloading, and you can see the power went down by about at least 75, 80 watts. And the behavior is different. It's not my focus to go into these performance numbers. I just want to show you that, yeah, offload does help. And when you look at the perf, then all the crypto numbers disappeared, right? Now you're hitting memory bandwidth problems, right? So now it's just copying to user space is your bigger challenge. Here is when we use TLS with a 16K record, essentially, 4 CPUs on server 1 versus server 2. Server 1 is the Cascade Lake. You can see that it's hitting 100% of the CPU of the 4 cores. At the bottom here, you have HTTP versus just user space TLS, ASNI essentially, then KTLS and KTLS offload. This line here shows you the throughput you end up getting. As you can see, with clear text, we're hitting like 43 gigabits per second we are actually using both 25 gigs. And as you go into NSNI, you can see that actually user space does better than the kernel version. But once you do offload, you're winning. And your power goes down and your throughput goes up, okay? And in server 2, which, sorry, I shouldn't have mentioned any names. These are two servers from with two different CPUs. You're hitting about the same number. We have some other overheads here that have nothing to do with the fact that we can do higher throughput. But of course, the performance, if you look at the performance curves, it's much better here because this CPU has much better design, is 3 years newer. And you can see the power utilization, we're hitting 420. This has nothing, this is not just the CPU that's consuming this, but also your PCI cards. And at the bottom, the green is the CPU utilization. How much the CPU consumes in terms of power. And this is both RAM and the uncore, it's the package essentially, right? So about half of that power has nothing to do with the CPU, okay? It's the other devices on your system. Same thing here, you're hitting about 175, but about less than 90 watts is what the CPU consumes. So it's not always the CPU, right? If you want to break it down for server number 1, with HTTP, you see all of them here. This is the CPU measurement, how much RAM is consumed, and the rest, right? So for this, we use this PTAT tool, right? Server 1, which is much higher performance. Sorry, server 2 is much higher performance versus server 1. And really the utilization this is server 1, okay, it's the lower end. We also try to run stress NG it's a different workload. It's not receiving a lot of packets. There's really not much difference between the two. If you go to the second one, I'll flip back and forth so you can see 88 watts on the left here, right? And now I'm going to flip to the next slide. It's over 200 watts, right? You're getting, if you were to take the throughput versus watts, you're getting much better throughput versus watts on server 2, but you're consuming more power, right? So, and the RAM is, DDR5 is much better than DDR4 on this machine here, right? So the point is we're not, and when you put it into idle, you can see that, again, this is one core where it's supposed to be two sockets. I'm sorry, we're only using one. But if we had put it two, it would probably hit like 50, 60 watts under C6. Whereas the other one is hitting about 93. And of course, the other peripherals are consuming about 130 watts. So point of our presentation here is to show that this is how you can measure things. You get yourself a PDU, you measure the system. You get yourself a tool like PTAT, you can measure how much the CPU is consuming. You can cross-reference against your PAF output. And you can collect nice graphs like this. And I think I'm going to stop there. Is there any question? Anything surprising here?
I'd also add that you can use TurboStat, the utility included with the kernel, to at least see what your CPU and RAM power usage is in real time from, and also the C-state usage. I was trying to mention it in my talk, but didn't quite get to it.
So you think thermostat would be an alternative to PTAT, for example?
Yeah, it's a simpler alternative, but at least it's there in all the kernels.
And uses the same tooling, basically.
Yeah, it's using the same backend pieces of the CPU, the thermal sensors and stuff.
Yeah, for sure. We'll give this a try. Those?
Yeah, do you know, have you tried digging deeper into why the server 2 peripherals use twice as much power as on the server 1? Because it's kind of, it may be obvious for the CPU. If you put another CPU, it will consume twice as much, but why also the peripherals?
Two sockets?
Yeah, this one here. There's some things I can say, but there are two different NIC vendors for one, between the two. This was an OCP kind of server. It had built-in stuff that we couldn't remove. We didn't dig that far, but definitely the NIC, some of the NICs and the optical that was in there had a problem. But we just compare the CPU utilization, right?
Yeah, it's okay. I'm just, I'm just curious why those numbers came out.
Yeah. So you're talking about the sum of the green and the CPU. So the green is CPU and the red is the total system.
Mm-hmm. Yeah,
Yeah.
but if you switch to the next slide, where you break down into the CPU and others.
Right. This one is for server 1 and this one is for server 2.
Mm-hmm.
Right. So 78 watts on the other stuff, or 80 watts, and 190.
Yeah, it's twice as much, basically.
Yes.
So that's... Yeah, but if you are extracting the CPU from this power, so the green part is everything else but the CPU, so the core count shouldn't matter there.
Are the network ports?
Sorry? Yeah, but it's included into the blue part.
Use the mic
at
if you
least
don't mind. The remote people can't hear you.
Or you can repeat the question.
Oh, yeah, sure.
Yeah, it's just saying there's uncore and such as well. So like there's probably more memory channels and all that also on the other CPUs. 'Cause if you go back to the original, I think it's what, like 56 versus, 112 versus 56, something like that. So
Yeah, what did you have?
Yeah, okay.
But Encore was included into the blue part, right?
Yeah, so that's the package
whole
right
package.
there. You
Yeah,
can
look
see
at the
the two
the
packages.
right side diagram. Is that server 2? Yeah.
It's
so
got a lot more peripherals.
It's got a lot of stuff.
There was actually one that didn't show up there because it was sucking power, but we did not expose the driver. So on the right-hand side, there was one the driver was not loaded, so it didn't show. Shrijit, then we go to Marcelo.
I just had a clarification question. And on your numbers, the blue and green graphs, it looked like the throughput was going up almost, 180 to 220? Or no, 180 to 220? No,
This one here?
Keep going, keep forward. The
Next one.
Yeah, the one with the bar graphs.
Yeah.
So you have 179. Throughput went from 179.51. That's throughput, right?
No, that's the total power used.
Oh, that's the total.
Yeah,
power.
so you see
Never mind.
88.98, for example,
Okay,
on
never mind,
HTP
yeah.
is CPU, and then memory at 11, almost 12. That's DDR4 versus DDR5 here.
Yeah, so okay, so you said that your power or bytes per watt got better. I couldn't figure out where
Yeah.
the bytes came from.
If you look at this and you take
I see.
how much power, how many bytes I got here, gigabits per second versus the power, if you divide that number, it's much better than this one.
I see.
If that's your metric, right? If your metric is bits per watt, you're definitely going to buy this server instead or deploy it.
And this is like, so you made a point, like if you're using optical versus copper, that alone could be a pretty big difference.
This one had an optical device we couldn't take out. This one, but that's reflected in this right? It's reflected in the other piece. It's reflected here.
Yeah, I'm saying it could get
Sorry.
even better if there was an optical bit. If you take that out, the optical SerDes are
Just take out the cables, you're saying.
depends. If your opticals are turning off, then yes.
All right, let's give.
Okay, so we're going to go next to Marcelo. I don't know if I can present his. Carl? There's a remote presenter. Oh, there was a question remotely, I guess. That was for you, Jesse, I think. But maybe we can take it at the end.
The question?
Joel
Yeah,
Samaro,
Joel had a question.
or a comment.
Yeah. He was interested in combining AI ML ingested with telemetry and wondering if such modeling would help to optimize power beyond seasonal trends. So my thoughts there is, yes, you could definitely use something to analyze the power usage there using AI. I believe the things that I'm aware of in that space is that there was some work from some people to do network tuning and power tuning based on with a machine learning algorithm. But there's going to be a lot of solutions like that can be made. It kind of just comes down to a question of how much effort are you willing to be putting in, and whether it's applicable to all workloads or not. And that's where it kind of comes down to, and all platforms and all kernels and all devices.
Okay, Marcelo, you ready? Yeah, he is, but Carl, can you take us off and leave him there?
And I'll stay without video. Sorry about that.
Sorry, you have slides, you said? Can you share?
Yes, I do.
Okay.
They are on your folder, it seems.
Oh, which folder, I'm sorry?
Not sure. I don't know. But I can just share here, and in any case, we can try yours.
Yeah, you should be able to share here. And just as a heads up, we have probably 20 minutes left. So again,
All right.
if there's interest, maybe we can have, actually, we can set up another meeting this week.
We had talked about having a little bit more of a chat around power like this maybe later this week on Thursday or something.
Yeah. I like your scheduler idea, by the way. So maybe that could be a thing we...
Something to pursue.
Yeah.
For sure. All right. Go ahead, Marcel.
Okay, thanks. So, hi everyone. I'm Marcelo, software engineer at Red Hat. I work at the Enterprise Linux networking team, and this is I studied that I did on ARM versus Intel networking performance and focus on power consumption. It's a quite initial experiment. So that's why ARM is advertised as more power efficient, and is that really so in our case here? And customers are considering these new servers, but how does it scale? How can we take, okay, we need 10 servers to cope with this workload, but when we switch architectures, how many servers do we need now? So this study includes TCP and UDP throughput performances, both are over IPv4. We measured CPU usage, system power consumption, and some initial analysis in the code on what was happening. Some notes on the lab. I had 3 different systems. One is this Ampere Ultra. It has 80 cores on it. Another it's E5, and then another one's another E5, but it has 2 sockets in the system. Both were there, so it's a much larger system. And running at a lower clock. All of them had the same NIC this time, ConnectX-6, at 100 gigabits per second, and all of them running the same Brownline kernel. On configuration details, to make the experiments a little bit more stable, NIC RQs and IPv3 tasks, they were pinned into dedicated CPUs, and respecting the cores on the x86, so one core for RQs, another core for IPv3, so they would have full power. And these cores are also isolated, so just in case anything doesn't steal any CPU time from it. And P states were just to always have the maximum frequency, but left the C states on. And this the configuration that was done through the TuneD to put performance profile. And without the C states on, we don't have fluctuation on power consumption, right? But at the same time, with it, yeah, you have some problems with test stability. So, test procedure. The test consisted on testing these combinations, these protocols, and in combinations on all these 3 systems. So one sending traffic to another with all the possible combinations that it had. UDP tests they had for small and M2 sized packets for 1500, and didn't use any special IPv3 parameters. So this is a sample of the results that I had. Hopefully you folks can see my mouse cursor. In this table, for example, the first one, the column on the left is the host that was receiving traffic, and on the right column, the host that was sending traffic. Netdevs, they are the ones on with Intel CPUs. And then there's the ARM one here. So in this case, it had 31 gigabits per second. This is the idle power that was measured. The test I measured with the BMC option that Jamal was mentioning. It's the most platform agnostic that I could find. And this is the power measurement that it had during the test. So we can see that it used 18 watts more while running this test, and here it used 22 watts more. A description on where the CPU times were spent, the amount of CPU that was actually used. So it is the sum of the idles, or better, 200 minus the sum of the idles. It equals this one, 200 because we have two CPUs, right? And then the two main metrics. It's the CPU percent usage here, divided by the throughput obtained, not the total traffic, but total data, let's say, just read it, the bandwidth. And the same thing for power. So in this test, Netdev 19 needed 4.7% of CPU to handle 1 gigabit per second. And it consumed almost 0.7 watts to handle this 1 gigabit per second. And while Netdev 89 needed 2.3% CPU to send traffic, which is usually much faster, it's less expensive, and also consumed less CPU to send that traffic. Now, if we have the same receiver but switch to ARM server that is sending traffic, the idle power on this system is lower than our sending one on the previous test, but at the same time it is higher than the Intel one. So it's things to get noted. And 21 watts increase during the test. And here, our ARM server was able to push more traffic than the Intel one. So the results on the ARM server when sending traffic was slightly better on the CPU percentage per gigabit per second. And it used a little bit more power. And then if we switch roles, something weird happened. Now ARM server is receiving traffic, and it maxed out on CPU usage. The two cores were fully busy. The throughput was considerably lower, 26 gigabits per second. It used way more CPU time to handle the gigabit per second, and way more power, like the double from the previous test. So now some quick graphs to have an overall idea. This we have a very visible difference here. This is the effect that I was talking about. This is all the combinations that the tests were done. Netdev 19 send the traffic to Netdev 89. This is the power consumption when sending and power consumption when receiving. So ARM here was really off the charts. And on CPU time per throughput, same thing, was off the charts. And the other ones, they look okay. No surprise in there. When ARM was sending, we can see that it was also okay. No surprises in there. All right. So when we go to UDP tests, also no surprises. We can see power consumption from ARM here and here. It doesn't go way off. This is one off that I still need to root cause. It's probably just a noise from the measurements, because when you enable power savings, things can go a bit unpredictable on this lens. And then when we go on 60-byte packets, we can see that when ARM was receiving traffic, it was much better than Intel regarding power consumption. And when ARM was sending traffic, it was also much better on these experiments. And regarding CPU time, it was also better here and here than the other ones that were receiving. A bit of a study on that interesting effect that was noticed on the TCP test. Apparently, on that ARM server, maybe some kernel configuration option or something. I couldn't get your root cause yet, but apparently transferring buffers from kernel space to user space takes way more time than on Intel, as noted here. And also some page handling shows up on ARM traces, which didn't show up on Intel. So maybe it's some opportunity of improvements in there. And these are studying the CPU that was running the application, right? And if we move to the CPU that was running the RQs, this particular function takes also quite considerable time more on ARM, and it just doesn't even show up on perf records on Intel. So maybe some other opportunity for improvements in there. So conclusions here, measuring power consumption for a workload is really not easy. When you enable power savings, the results they are not stable. You are more prone to hit situations like the number of retransmissions that TCP kicks in, they are different. When that changes the amount, changes the result. It's hard to find a way to measure power consumption across very different architectures and platforms. And we get even to the point that how do we deal with power supply efficiency change? Because when we are running at idle, you're probably running in a point of the power supply that it is not as super efficient. Like it's using more power than it is actually providing to the server. And when you add some load to it, it runs smoother. It has less waste in the power supply itself. It's like a car when you're driving on high halves or more efficient. So these are questions that I'm still battling with them. And out of these tests, TCP receive seems weird and needs more digging, while TCP send and UDP send and receive, they seem to be okay. So that was it.
Yeah,
if you have any questions, thank you.
I'm sure there are questions. So it wasn't clear to me. I mean, you're saying ARM doesn't do that great in power, and I always map ARM to be the king of power, or that it would do very well. Or maybe I missed your message. At the beginning you're showing, was that x86 was one of the slides, I think, versus ARM? And I wasn't sure that your reasoning was maybe a badly written driver that didn't take care of issues that ARM may have or not?
Yeah, maybe. Yeah. I still need to get to a root cause on that effect. And there's also the question on how can we make this comparison fair? Because which server, which let's say Intel CPU should be used to compare with this particular ARM one? Should I turn off the remaining cores because this ARM one has almost double of the cores of the biggest server here? So these are open questions that I'm still going through them.
I think that's a great question, right? Like, how do you even compare? And not only that, but you're probably going to be ending up messing with like how much cache each CPU has and how much RAM each platform has. So, and then there's all sorts of, complexities of the platforms like Jamal's example showed. right? When you have a whole bunch of I/O devices, they may be sitting there just, sucking power.
So I can say that one thing we did, Pedro, I think we turned off all the CPUs but 4, right? And we still got the same numbers. We got the same power. That's why I think the package power management is very smart. We turned off 52 out of 56. We powered them off, but it still consumed the same amount of power, give us the same performance results.
The one thing I wanted to
We have
add
some
was we have to be a little careful about saying this is ARM performance. This is Ampere's performance, right? This is an Ampere CPU. How did you, have you run on any other ARM platform to see if there is a correlation?
Like a phone?
No, ThunderX. There were others. Yeah. There is a Grace coming soon, I guess, from NVIDIA. There are other platforms out there. Is there, what would be interesting to see is there an ARM system implementation issue? Like you were saying, if paging is showing up, or if processor placement is showing up, or if the gap from DDIO is showing up, that would explain a significant amount of ARM-specific issues. But otherwise, it could be an Ampere platform issue as well.
Right, Shurjit, agree with you. I should have named it after Ampere and not ARM. And yeah, this can be bad driver code, bad driver code, or bad architecture code. I still can't point what it is.
I'll read it. Marcelo, I'm not sure if you can see this question. Did you look at the workloads with the mix of CPU plus I/O? Are you interested in comparing ALU instruction mixes between architectures?
So I did not look into that yet, but in the future, yes, I am interested.
Yeah, I'd be also wary of these benchmark workloads since they're doing very little work in user space with the data. You're simply copying the data to the user space and discarding it, so it's never actually hit and warmed up in the cache if it needs to be. This can cause some really weird artifacts in my experience. So just be careful about not consuming the data and making a comparison or judgment based on it, because if you were doing SSH traffic for TCP, it'd probably be a way different sort of measurement.
All right, thanks.
One question from me. So something that came up in my work is, did you isolate or turn off Intel DDIO? Because when I ran on Intel systems with DDIO with iPerf 3, it's kind of like the perfect benchmark. It doesn't do anything with the data. It just throws it on the ground. And Intel DDIO is like the perfect fit. So I wonder if that's explains some of the kind of discrepancy between Intel and ARM, because in your perf profiles, you saw that a lot of time was spent doing. Yeah, exactly.
Yeah, so he's referring specifically, your question is referring specifically to whether or not Intel's DDIO helps on workloads, and these benchmark workloads for sure it does, and you would be able to actually count that, Marcelo, by looking at the perf counters for cache hit ratios when it was, there's some specific DDIO counters that show when the cache is being used or when you're seeing cache misses, in fact. And so those counters are very visible and viewable metrics in perf that will help you determine whether or not DDIO is being used or not. I'm a little bit surprised to hear that you could say you could turn off DDIO, because usually that option isn't available.
You can, yeah. There was actually a paper in, I think, Usenix, like a couple of years ago. A bunch of people figured out there's a bunch of magic registers you can write to actually turn off DDIO. And when I did it, I could see the difference in system memory bandwidth.
So 5,000-page manual and find the right page, right? Yeah.
I think it was actually completely not documented. They managed to reverse engineer this somehow from.
There may be some leftovers from the past, but yeah, the DDIO is usually pretty, from my experience, it's just there all the time. But you can tell it's not there on client platforms, because Jesper was doing lots of measurements on client platforms and he was not seeing any benefit from DDIO. No big surprise, it's not there.
Right.
Yeah, the one thing I was going to say is actually his data already kind of points to DDIO as being a difference. Because if you go back to the one slide where it was the ether prop in the Mellanox driver showing up.
Yes.
It's most likely inspecting the Ethernet header, and it's probably a cache miss on the start
Right.
of the frame. So that's most likely what's
Right.
triggering that.
That would be nice and warm cache line with DDIO doing its
Right.
thing.
Yeah.
The,
It'd be
the
right
other
there.
thing I was going to mention is one thing for those systems that don't have it. I think Eric pointed out in the last Netdev, there's the TX no cache copy that Tom had added several years ago that actually is showing benefit for 100 gig workloads when DDIO is not present. So that might be another thing Marcelo might want to take a look at in terms of turning that on the AMD system to see if you can get additional throughput by bypassing the cache.
Yeah, the ARM system, right?
Yep.
Yeah, thanks, Alex.
Okay, thanks, Marcelo. Is there any more questions about the topic in general for power management or Marcelo? Because I bet everybody's pretty tired.
Yeah, I think this shows there's interest in this topic. So Jesse has sent that mailing list.
Yeah.
We will have more discussions if there's interest during the conference. Thank you.
Thank you.